Hello everyone and thank you for joining us. In today's webinar, we will be discussing about one of our product HFWorks. We will simulate RF-induced heating of passive implants during MRI using HFWorks tool. Before discussing today's agenda, let me introduce ourselves. My name is Ehsan and I'm a sales engineer in our company. And we will have my colleague Asma, who is a senior application engineer in HFWorks. She will be delivering the technical part of today's webinar. During the presentation, if you have any questions, please feel free to use the chat window box to type in your question. We will answer them at the end of the presentation, or we will reply to you via emails. Also, the webinar recording link will be sent to all of the registrants and attendees in few days. Our agenda for today is following. I will briefly talk about our company, HFWorks, where we are located, and what products we offer. Then my colleague will present the technical part. At the end of the presentation, I will talk about various learning resources offered by HFWorks for its software users. HFWorks offers 3D and 2D electromagnetic simulation software as an add-in tool for SolidWorks and Autodesk Inventor 3D CAD. Our company was founded in year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solution and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of electromagnetics. Our products are gold certified by Dassault System SolidWorks Corporation since 2008. We have 2 office locations. Our headquarters is in Montreal, Canada, and another office in Germany. We offer 4 products with various add-ons covering a wide range of frequency. Our first product is called EMS, which is used for electric and magnetic field modeling for low-frequency applications. It covers many applications like insulators, cables, bus bars, permanent magnets, actuators, circuit breakers, transformers, and motors. Second product is HFWorks, which is used for electromagnetic simulation of RF, microwave, high-frequency, and high-speed electrical and electronic devices. It covers applications including wide range of antenna, resonators, filters, connectors, waveguides, and etc. Our third product is HFWorks 2D, which offers static analysis and covers simulation of planar and axisymmetric geometries. Our latest addition is Motor Wizard, which is a template-based motor design software. It offers analytical and finite element analysis of BLDC and PM motors. In addition to these solutions, we offer few multi-physics solutions as well, like thermal, motion, linear statics, and circuits. In today's webinar, Asma will utilize HFWorks product to simulate RF-induced heating. I would like to ask Asma to take over and
Thank you, Ahsan.
start
Hello, dear attendees.
her
First of all,
presentation.
I want to thank you
Thank you.
all, our faithful attendees and our new participants, for joining us today. I am Asma, Senior Application Engineer at HFWorks, and today I'm going to represent you the technical part of today's webinar about simulation of RF-inducing heating of passive implants during MRI using HFWorks tool inside SolidWorks. So from the title, we can clearly release that in this webinar, we will cover the topic of magnetic resonance imaging, and we will try through it to provide you the main challenges and side effects related to human exposure assessment to electromagnetic fields radiation during magnetic resonance scanning. In particular, the capabilities of HFWorks S-parameter simulator will be demonstrated by showing examples of SIR and also thermal effects of the studied MRI on biological human body with medical implantable devices. First of all, let's have a look on our agenda for today. We will start with a small introduction about MRI systems and what are passive medical implants. Then, we will move to an overview about HFWorks inside SolidWorks with a quick live demonstration of the software's interface, features, etc. Next, we will go through a detailed analysis using HFWorks simulation solution to investigate the studied 1.5 Tesla MRI birdcage coil design operating at 64 MHz and its performance in free space and also when a human body phantom design with the medical implants is placed inside it. Finally, a conclusion. Now let's start by our introduction. As you all know, magnetic resonance imaging is a medical imaging technique which uses strong magnetic fields, magnetic field gradient and also radio waves, allowing to provide excellent resolution scanning of the orgasm in the body. The MRI machines available today have field strength ranging from 0.1 Tesla and lower and could reach 3 to 7 Tesla for some types which produce the clearest images. There is a wide range of MRI machine types designed to serve different purposes. Apart from the Tesla strength, MRI machines are differentiated into 3 high-level categories based on their structural size and design. This includes the closed MRI machines, the wide-bore MRI type, and also the open-bore type. For the first type, the closed-bore MRI, are usually high-field systems that have excellent image quality, speed, and magnet strength ranging from 1 Tesla to 3 Tesla. They are coil-based designs. They could include the Helmholtz coils, the birdcage coil design, the gradient coils, etc. For the open-bore MRI, they use permanent magnets in their C-shaped or H-shaped configurations. They operate at field strength typically ranging from 0.064 Tesla to 1 Tesla. And finally, the wide bore, which combines the benefits of the open bore and also closed bore type. For all the mentioned MRI designs, HFWorks products including HFWorks for high frequency and EMS and HFWorks 2D for low frequencies, they offer a complete and accurate solution for MRI electromagnetic analysis to compute the MRI coil circuit parameters like the resistance, the inductance, the impedance, etc., the magnetic and the electric field distribution, the RF and induction heating, the SIR, etc. As already mentioned, magnetic resonance imaging is an essential imaging modality. However, with the growing number of MRI machines as well as medical device implantations, there is need to assess the safety of MRI scans. Most of the medical implants are made from metallic materials and could be passive with no powered electronic components, which will be used in our simulations, like the orthopedic types for hips, knees, etc., the cardiovascular type using stents, valves, and so on, and for the neurovascular components. We have also the active implants with powered electronic components, like the cardiac simulators in case of pacemakers, the neurosimulators, and drag pumps, sensors, and so on. Now, before moving to simulation part, let's start by introducing our software for our new attendees. HFWorks is a 3D field simulator fully integrated inside SolidWorks for RF, microwave, and wireless applications. It is an add-in inside it, allowing the user to work on both CAD and simulation within the same interface. HFWorks covers a wide range of applications such as antenna, for the printed types, the waveguide, the on antennas, the wired, etc. The S parameters for filters, oscillators, matching circuits, waveguide twists, directional coupler, and so on. The time domain, reflectometry analysis, and finally the resonance analysis for dielectric resonators, etc. HFWorks comes also with an integrated electrothermal, steady state and transient analysis for electronic products, ensuring their electrothermal reliability, which is available for antennas, S parameters, and TDR analysis. We move next to introduce our studied birdcage MRI coil design. Birdcage coils are a type of volume coils which are widely used for MRI applications to provide homogeneous magnetic field. Also, when this particular birdcage coil is quadrature fed, the field homogeneity is improved. So, our 1.5 Tesla static field low-pass MRI design operates at 64 MHz and it consists of 16 parallel conducting strips made of copper, colored rings, surrounding by two circular end rings with diameter of 65 cm and total length of 57 cm, and equipped with 16 capacitors of 3.5 picofarad for low-pass design. Quadrature feeding is used to achieve an homogeneous magnetic field through two excited spots with 90-degree phase shift in excitation and also in position. The CAD part is done using SolidWorks. But before moving to the simulation and results, let's have a quick demonstration of HFWorks interface inside SolidWorks. So here we are. This is our SolidWorks interface with the birdcage coil design and also outer surrounding air. We can hide it. So as we said, HFWorks is an add-in inside SolidWorks. So if we check from here the add-ins window, we can found it here. Once it is checked, an HFWorks tab manager will be added automatically with all main features. And also from this interface we can create your analysis and also run it. For those who already attended, they may know that, but for our new attendees, we will try to create new study from scratch. We already have create study here, but let's start it from the beginning. Just right click study and you can choose your study types. As we already mentioned it, we have the antenna as parameter, TDR and the resonance. For our case, we will create a new S parameter study, just clicking. A property manager page will be opened. We have some properties to settle for our study. So we start with general properties. We have the name, we have here the solver type, many solver types, the direct solver, the iterative solver, etc. We have the accuracy solver type, normal and high accuracy. We have some options like here if you can create a study with parameterization. Also, if you want to check only the port solution or to check also the 3D field data, etc. Once we are done with this step, we move to the next step for frequency sweep. Actually here the default frequency setting is single point, but we can change it to fast sweep, discrete sweep, etc. We have to set your initial frequency, start frequency, end frequency, and number of frequencies. Once it is done, we can check your frequency list from this grid data. Next, we move to the meshing, from where we can choose your meshing type. Manual meshing with your user-defined mesh controls or with adaptation, with many features here. Then we move to the last tab for coupling analysis. As we said, HFWorks is enable the electrothermal analysis for with steady state and transient thermals. So if you wanna add an thermal analysis, you have to check this one, and you validate. So a new study will be created. So we have, as you can see here for this new study, we have 3 different sections. We have the materials. You have to start by assigning your materials, just clicking on apply. A well organized and rich library will be opened. You have to just choose your material, then validate it. Also boundary conditions, we have a list of boundary conditions according to your study type. We have wave part, lamped board that we will use for our case. We have PEC, IEC, etc. And finally, the meshing step. You can create your mesh, the automatic mesh with the default setting, or just add some mesh controls in case of adaptation. Also, you can create your adaptation study based on existing mesh with user-defined mesh controls. Once all of these steps are done, you have to just right click and run. For the thermal solution, it is a post-processing analysis, so once the electromagnetic is done, you can create your thermal coupling case and with the thermal boundary conditions and solve it separately from your main electromagnetic part. As we said, we have here already created study and solved. This section of results will be added automatically after the run is done. We have some results here. We have the electric field distribution, the magnetic field intensity, losses, volume losses, and the dielectric losses and also the conductor losses. Two types here, volume losses for dielectric and surface loss for conductor losses. We have a calculator here to compute your total loss. You have to just right click, compute losses. If you can see here, if you want to, for example, compute losses in our bird cage design, just clicking, put your input power, a phase, and click on compute. We have dielectric losses, conductor, and the total losses. Also for port fields, we have here the electric field port and also magnetic field. And finally circuit parameters. If you want to check the S11 results, you have to just right click to deplot. Select your type of results, S11 like here, add, and the plot will be opened automatically. So we'll move now to analyze these results. We come back now to our presentation. We have here the return loss result for the studied birdcage MRI design. As we can see, the different resonance frequency between 10 MHz and 120 MHz. In our case, we are interested with the 64 MHz, with the high return loss greater than 25 dB. The right figure is showing the Smith chart plot for the same frequency band for the S11 results. Now, since we are interested to evaluate the MRI scanning of a human body with implantable devices, we will use for the second simulation standard ASTM human phantom with the metallic hip implant. ASTM refers to American Society of Testing Materials. So it will be used as a human body approximation, since current ASTM norm on testing medical replacement towards MRI RF heating only recommends the use of such phantom for experimental and numerical simulations. The dimensions of the used gel phantom are fixed by ASTM norms and consists of a plastic container with geled saline. This geled saline will replace the human body materials with equivalent material properties. And also we will use stainless steel hip replacement. Here we have the phantom gel with permittivity of 80 and conductivity of 0.47 Siemens per meter, mass density around 1060 kg per cubic meter. The first results are for the case of a human phantom without adding the implant inside it. The turn loss curve versus frequency of the studied MRI with and without a human phantom are shown by the next figure. The red curve is for the MRI return losses in free space, and the black one when adding the human phantom. A tight shifting is noticed with the same resonance frequency. Now for the electric field distributions, for an input power of 100 watt, and when exciting both parts with the 90-degree shift, it achieves a maximum field around 120 volts per meter, and the temperature increases with 0.85 degree inside the phantom gel, which is very acceptable temperature increase. This is for a heating period of 15 minutes using a post-processing transient thermal solver of HFWorks. Now when adding the metallic hip implant, we can notice that there is no big effect is added to the return loss results. But for the case of electric field distribution, which is shown by the left figure, an increase to 315 volts per meter is noticed around the metallic implant, followed by a significant temperature increase of 4.3 degrees Celsius after the same period of 15 minutes of heating. So, the medical implant is characterized here by with two hot spots in the top and the bottom of it, which may cause tissue burns in case of real biological body and could cause serious hazards. As we can see, the temperature rise follows the behavior of electric fields where it is concentrated. Let's compare now the second important results, which are the SIR, the specific absorption rate distributions. As clearly noticed, the presence of metallic replacement highly affects the human tissues by increasing the rate of absorbed energy inside it, which are converted later to heat around these implants. The obtained local SIR results distribution exceeds the limits defined by STM norms. We have 3.48 watt per kilogram for human phantom without the implant and around 100 watt per kilogram with the human phantom with the implant, which is a very big difference, which explains the high increase in temperature around the implant device. Now we made small testing. We changed the implant material with the most used materials for this kind of medical devices, and we try to check the effect of it on the RF heating rate inside the phantom. So, as you can see, the temperature rise is always bigger than 4 degrees Celsius. For the three selected metallic materials, the stainless steel, the cobalt alloy and the titanium. Now, for the next step, we will try another frequent used passive implant, which is the cardiovascular stent. It is placed in the central side part and placed 2 cm from the phantom wall. This location provides a high uniform tangential electric field over a length of approximately 15 cm. So, as a result of it, as we can see, the return rate results are not far from the hip implant results as shown by the left side when they are compared with the MRI performance in free space. The electric field is also very high around the metallic stent and achieves high levels to exceed 620 volt per meter, and also for the local SAR distributions, which achieves 136 watt per kilogram, which is always very high. So from these results we can predict how will be the temperature distribution too. Here we have the dielectric loss density distribution and the temperature rise, which is around 3.5 degrees Celsius around both stent sides. These results are considered high and insecure for a human body for an MRI scanning period of 15 minutes. So even with these small devices, the generated RF heating by MRI could cause huge damages on human tissues. So the following 2D and temperature distribution animation are demonstrating the temperature increase step by step versus time. Those results are for a heating period of 15 minutes and could be longer according to the type of the scan done. With the same stent device, HFWorks tool allows also to predict the effect of the stent position inside the phantom using a parametric analysis by changing the distance from the phantom center to the stent center. We got the following results. In the left figure, we can see the maximum achieved temperature rise versus distance after 15 minutes of RF exposure. It is clearly noticed that highest heat rates are obtained when the implant is positioned at the center. The right figure is an animation of the 3D plot of temperature distribution versus the different studied positions. This is another important factor that also affects the amount of RF heating inside the human body. We move now to the last part, in which we will try to approximate our simulation to the real conditions by using real human skeleton geometry inside biological tissue with the first hip implant that we studied with the rectangular ASTM phantom. For the tissue, we will keep the same properties as gelate saline, And for the bone part, we will use the following properties. A first run is done using rectangular phantom with skeleton geometry as shown. We got the following results. The maximum electric field is localized around the implant bottom point with the value around 450 volt per meter, and the local SIR follows the same concentration points to achieve a value of 20 watt per kilogram, which is lower compared to the Eastern phantom. An increase of 2 degrees Celsius is obtained in the bone tissue. Finally, when we use the human body part with the skeleton, we can clearly notice that the temperature increase is lower than the previous tests. This could be related to many reasons. One of them is that the bone conductivity is lower than the phantom. So it is important to mention that the use of an homogeneous human body model with all main tissue materials could reveal what will occur inside a human body during MRI, which is possible to be done using HFWorks simulation. We conclude now with these results. So, during this webinar, we saw how HFWorks presents a powerful tool to analyze and investigate the human interaction with radiated electromagnetic fields inside MRI machines. MRI safety evaluation for medical device is a global concern that counts on the numerical simulation to predict the amount of RF heating to avoid human body results. So, numerical simulation is one of the keys to a safe MRI scans for everyone. Finally, thank you all for your attention, and I hand over again the screen to my colleague.
Let us briefly touch upon the licensing structure offered by HFWorks. We offer 3 different programs: commercial, academic, and a startup program. Each program has its own benefits and requirements. Within commercial program, we offer perpetual licenses, while in the rest of the programs, our licensing structure is usually annual based. HFWorks offer various free learning resources. With the software purchase or trial, users can access the demo viewer section of the software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our web page and social media channels regularly. We also offer paid customized training sessions to all your users of HFWorks software. I encourage everyone to try our software and experience its capabilities. Upon trial request and user qualification, we offer 2 weeks of free access to the limited version of software. In this limited versions, users can access many predefined model examples and tutorials to learn about the software, features, and capabilities. To request for a trial license, visit our webpage www.emworks.com, go to our Contact Us page, fill in your information and submit your request. One of our representatives will reach out to you. I would like to thank you all on behalf of HFWorks for participating in this webinar. Feel free to contact us after this webinar to get more information on our products. Thank you very much.